In the last video, I looked at deriving the exact drop formulas for the arc and horizontal distances. In this video, I'll do the same for the chord length, and by doing this, we'll easily see where the 8 inches per mile squared rule comes from. We still have the observer position P and the target T, and you can see that these points are now also separated by a chord with some length C. Notice these two right triangles are similar. Sine alpha at C is the opposite side over the hypotenuse, or half the chord over the radius, and we can simplify that to C over 2r. Sine alpha at T is also the opposite side over the hypotenuse, but this time it's simply the drop distance over the full chord length. That gives us this equation, which can be rearranged to give us the exact formula for the geometric drop when using the chord distance as the input. Writing that as a constant multiplied by the chord distance squared gives us this for the drop distance in miles, this for feet, and this last one puts the drop in inches, which works out to about 8.0025 times the number of chord miles squared. And as the distance along the surface isn't that much longer than the chord length, we can see here that it's not even a foot longer at 41 miles, and only about 14 feet longer at 100. We can confidently make the drop rule 8 times the number of surface miles squared, without introducing too much error. So how accurate is this approximation? Let's compare it then to the 3 exact formulas we've gotten so far. These are the 2 we got in part 3, but going forward I want the main focus to be set on these 2 rows, the approximation versus the arc length. For a target distance of just 1 mile, we have 8 inches or 2/3 of a foot of drop, showing here to 2 decimal places. And at 6 miles, there's just a grain of rice between the drops. Now, do you remember this photograph of Blackpool on the Lakes by Kevin Jackson? Well, I put the camera just over 12 miles from the tower and just over 50 miles from Doe Crag, and that's what the next 2 presets are about. For the tower distance, there's only a pencil width between them, both giving a geometric drop amount of about 99 feet. At the distance of Doe Crag in the Lake District, the difference in the drop value seems to be growing, the approximation now underestimating the exact value by about 6 inches. There's not even 2 feet between them at 100 miles, but when we get to 172 miles, the approximation seems to hit a limit of just over 3 feet of drop under the true value. After that, the difference starts to shrink until the distance reaches 243.1 miles, when the drop from the approximation is near perfect. Keep an eye on this number. So the difference starts off small. It gradually gets bigger to about 3 feet, and then it starts shrinking again. Practically the same. Beyond this point, the drop rule becomes an overestimate, and the difference grows quickly to the point where 8 inches per mile squared is no longer useful. At 1,000 miles, the percentage error is only half of 1%, and that doesn't sound like much, but in absolute terms, it's 3,329 feet. And you might hear some saying that the 8-inch rule is accurate to about 1% at around 1,400 miles. And this is quite true, but that 1% translates to nearly 13,000 feet of error. That's taller than Mount Fuji. I guess this is one of those times when a 1% error sounds far better than it actually is. In the next video, I'll look at how atmospheric refraction changes things. See you in part 5.